Hello, hello. Welcome to the day. Welcome to day 4 of the journey. The first 3 days we have implemented our first triangles, rendered our first triangles, and the result of these first three, this image, this um, the coloring. We would love to change the coloring. Couldn't manage. I will not go deeper into that today. I will simply the different coloring and triangles. I simply all fragment color value orange. When I compile it again and start it again, we'll have all orange triangles. Yes. Originally, we or started wanting to display a pizza shape, but it didn't work, so we couldn't have enough vertices. So we have ended up displaying a shape like a wind turbine. So now I would like to search something. It's called that is called um hub, and I want to research if if I can if I can generate vertices and indices using what do you call it, uh using writing. I mean, convert writing into vertices and indices. Hmm. Let's see if there is something like it. Have you seen the Learn OpenGL page on text rendering? Blender can generate 3D text, but can we export Blender models with vertices and indices? Because if we can do this, I would like to model something else. Vertices and indices. Okay, let's see. Necessary cookies on their way in Blender to export vertex coordinates as a numbered list along with a vertex to vertex edge list. I'll show briefly what I'm talking about. Yes, I want exactly this. What? So does that mean if I create something in Blender, Blender, I create something in it. It's better. Yes. I mean, I don't know. It's general. Let's see. If this, my question is if I can export this as vertices and indices. What do we have here? If we export it as an OB, it's Windows 3 childish dev modeling. Export it. Let's see. Um, go childish dev folder, modeling. Here we have our element, and I would like to see the content. Nice. This means, I guess, we have vertices for the cube, and I don't know what these are. Let me see. What are these? Are these? Are where is our blender again? I see. Yeah, I don't know how import this. There should be model importer for this kind of questions, but actually don't know. See in op.data is what file extension. File extension. I can try now. That does not what add-ons are the add-ons. Get far here, I guess. Let's see. Let's keep going on the tutorial. We could display something other later. I'm sure we will explore the models. Yes, here in the model loading chapter of the tutorial, we will handle those. Take one step at a time and keep going on with shaders. Yes. I'm reading it and implementing it after. Mentioned in the Hello Triangle chapter, shaders are little programs that rest on the GPU. Programs are run for each section of the graphics pipeline, and in a basic sense, shaders are nothing more than programs transforming inputs to outputs that we have seen these. Our vertex shader got as input the positions of the vertices, and as output it spit out the positions as so it just passed through the positions of the vertices passed through the shaders, and as process we have set the GL position to the positions of the vertices we have got. In this section it will be explained, I guess, how to use them a better fashion and how to implement them in different files, in other files other than the string variant here, I guess. Let's see. GLSL shaders are written in the C-like language GLSL. We have seen how the GLSL looks like. Looks like something like this. Like it says, it's a like language, and it seems a bit weird, but yes, this is our life, I guess. GLSL is tailored for use with graphics and contain useful features specifically targeted at vector and matrix manipulation. Shaders always begin with a version declaration. We have already seen how version declaration is done, followed by a list of input and output variables. These are, like said, the input and output variables. uniforms. What are uniforms? We don't know yet. And the main function. The main function, I guess, the main function is the entry point, and is only execute is the only thing that has been executed in a shader code. Where we process any input variables and output the results in its output variables. Don't worry if you don't know what uniforms are. Okay, we don't know what uniforms are, and we are not worrying. A shader typically has the following structure: the types and input declarations, input declaration, the type of the input, and the variable name. Output is declared similarly, I would say, and uniform is declared also similar. We have learned what input and output parameters are, but not learned what uniform parameters are. And when we're talking specifically about the vertex shader, each input variable is known as a vertex attribute. So in a vertex shader, you can't get anything other than vertex attribute as an input, as the input. There's a maximum number of vertex attributes we're allowed to declare, limited by the hardware. OpenGL guarantees there are always at least 16 4-component vertex attributes available. So it means I can write only 16 times the vertex, the vector for position. Only 16 times. Okay. At least, sorry, at least type 16. What is this in number attributes? GL get integer v l max vertex attributes written in number attributes should yield 16, but it yields the minimum. Okay. Types. What are the types? We know some types. The vector 3 is a type. Vector 4 is a type. We have seen it in the output parameter, and also the we didn't see anything, but I'm guessing we can input anything we want, ranging from vectors to floats to input integers. I'm guessing, but we'll see. Okay. Oh, it's right. Okay. The LSL has most of the default basic types we know from languages like C. It has int, it has float, it has double, it has unsigned integer, it has boolean values. But it also features two container types that we're using a lot, namely vectors and matrices. So we can also define a matrix. That is fine. That is really good. Matrices will be discussed later. What is a vector? Vector is a 2, 3, 4 components for tuples that are represented in the as in a group together. They can take the following form: the default vector of n floats, so 2 to 4, and there is also a Boolean vector. There is also integer vector, and there is also an unsigned integer vector. And finally, there is also a double vector. Most of the time, we'll be using the float variant, it seems, which is sufficient. Okay. The components can be accessed via XYZ, XYZ, Z, XYZ, and W. We could also use RGBA for the color vectors, I guess, and STPQ for texture coordinates. Okay. They're basically the same, I think. If you use X or R or S, it shouldn't matter. The vector data type allows for some interesting and flexible component selection called swizzling. What is swizzling? Allows us to use syntax like this. So you mean the vector dot xyxx is a way to write another vector which is created from the first and second components of a vector. Okay. It also enables us to create something like this. I mean, we have a vec4 constructor here and a vec2 argument here, so we don't need to pass in 4 arguments, but we can pass in 3 arguments. Simply you would expect 4 arguments from a vec4 from a vec4 constructor because it has 4 values, but by simply passing in a vec2 as a parameter, we are simply hitting 2 birds with a 1 stone, I guess. Okay, vectors are thus a flexible data type that we can use for all kinds of input and output. We have learned a lot about vectors right now, how we can use them, what they are, and how they are created. Ins and outs. What are ins and outs? Shaders are neither licensed programs on their own, but they're part of a whole. And for that reason, we want to have inputs and outputs. Sure, what is a program without input and output? On the individual shaders so that we can move stuff around. GLSL defined the in and out keywords specifically for that purpose. Each shader can specify inputs and outputs using those in and out keywords, and wherever an output variable matches with an input variable of the next shader stage, they are passed along. So you have to match the naming. So you have to, if you are typing here out vec3 position, you have to match it in the next shader. So if you define an output variable in a vertex shader, you have to match it in your fragment shader if you want to use it again in fragment shader. Sorry. This is, in my opinion, a bit important because yesterday I have written here int vec3 pos, which then which then yielded an error. So we shouldn't do that again. Where was I? The vertex and fragment shader differ a bit though. The vertex shader should receive some form of input, otherwise it would be pretty ineffective. So, what vertex shader does is it gets the vertex input and it manipulates these vertex inputs so you can see it, so the OpenGL can render it. Differs in its input that it receives its input straight from the vertex data. So you have to put a vertex data in the vertex shader. Define how the vertex data is organized. We specify the input variables with location metadata so we can configure the vertex attributes on the CPU. We have seen that in the previous section of the tutorial. We have to write layout location 0 equals 0 here in order to pass our vertex data using this method. Can you see? No? Can you see? Yes. Using this method, GL vertex attribute pointer. Yes, the shader. I do this. Documentation. I need to search online for the document. Never mind. Let's keep on. So we have to define. Okay. Never mind. The vertex shader thus requires an extra layout specification for its input, so we can link it with the vertex data. It's also possible to omit the layout location specified and query for the attribute location in your OpenGL code via GL get attribute location. So it means Please. Yes. So the LJet gets attribution location retrieves the assigned vertex attribute location of a given shader program. So you give a shader program and you give the name of the int. Okay, then it returns the location is an integer. And after that we are using the GL enable vertex attribute array. So this one, can you see it? This one finds the array that we provided with the input of the vertex shader. Yes. So, okay, we have understood until this point. We can continue. The other exception is that the fragment shader requires a vec for color output variable. Requires it. We have to put it in. This fragment shaders needs to generate a final output color. If you fail to specify an output color in your fragment shader, the color buffer output for those fragments will be undefined. It will either be rendered black or white. So if you want to send data from one shader to another, we'll have to declare an output in the sending shader and a similar input in the receiving shader. And the types and the names are equal on the both sides. OpenGL will link those variables together, and then it is possible to send data between shaders. This is how we experienced it. To show you how this works in practice, we're going to alter the shaders from the previous chapter to let the vertex shader decide the color for the fragment shader. So you mean vertex shader is the vertex color and the vertex color. Oh, we could have done that actually. Instead of passing on the vertices, we could have set our vertex colors in vertex shader and then pass them on to our fragment shaders. This is a nice insight. Mhm. So the vertex color gets its color in the vertex shader, and this is an output variable. It is shared with the fragment shader, and the fragment shader simply sets the output variable to this input variable, which is pretty straightforward, I would say. And the vertex color then gets its color from this code. Yes, which is RGB half red. There we go. Okay, we have done it already in our previous section by simply sending the vertex positions to the fragment shader, and we have used it there to define the how they call it, define the color, but we couldn't get it good. The solution, the results were not uh, as we wanted them to be. So, what are uniforms? We wanted to learn what uniforms are, and we're learning what uniforms are right now. Uniforms are another way to pass data from our application on the CPU to the shaders on the GPU. Uniforms are, however, slightly different compared to the vertex attributes. First of all, uniforms are global. So simply, I'm not calling it yet, but I want to call it, the uniform variables are global variables. Global meaning that a uniform variable is unique per shader program object and can be accessed from any shader at any stage in the shader program. So it means, second, whatever you set the uniform value to, uniforms will keep their values until they're either reset. So they are simply global variables which are transferred through the pipeline until the end, and we can alter their values to whatever we want, and we can read their values in whatever stage we want. This is simply it. And how are we declaring it? Not a surprise, we are declaring it as uniform, the type and the name. Yes. Simply the color is uh, uniform here. Our set is set uniform here, and if we define, this is fragment shader, and if we define it in the vertex shader too, we can set it in the vertex shader to a value, and then we could simply read it in the fragment shader, the other value. What is this? Yes, it's. I'm going to take the break here from the tutorial, and I'm going to experiment with the uniform shade, uniform variable here, um, instead of declaring the position as an input variable here. I will declare it as the uniform variable, vec3 position. And also declare it here on vec3 position, and I will simply, instead of getting all the absolute values, I will simply set my fragment color, my output variable, to the uniform position. So I will set the color in vertex shader, so to say, by using the not by using the uniform variable. That. What am I typing right now? I don't need the code here. This code here, position equals false. I need it because I have to set the uniform variable. No, I don't need it because it will be color. Sorry, it will be color later on. I can set it here actually. I will get apps. Do I need those? I will just. Uh, and here fragment color will be set into the position. The naming convention is not the best here, but I'm try something. I'm trying to experiment with something. Yes. Here, type vec4 here because position is a vec4 and the pos is a vec3, so call it like this, and it will be position will be created. So here each vertex will have um, the the color of the color of the color. Each vertex will set each vertex will get its color from its position. Yes. So, but I want to actually use absolute values here because, like, I don't know what the behavior is if I use any what do you call it, if I use any negative values in the colors. So I'm going to simply calculate the abs x and abs y of the position pos of the input variable, and I'm going to then create my vec4 using the abs x, abs y, 0.0. I don't want any blue shades, and 1.0 f. So position, the output color is set. Yes. Sorry, I hope this works. Let's go. Let's build it. It has been built. Okay, we don't see anything because assignment. have here? Fragment, vertex compilation failed. Assignment to uniform position. Why can't we assign it? Oh, I guess not. I guess we cannot set uniform variables in the shader code. This is news. What is this? Oh, color change. This is news. So yes, this is news. So our code didn't function as we wanted because we have used this line to set the uniform variable to another value, and that we can't do that because it's not allowed apparently. I'm commenting these lines of code out and I will see how it works. And probably it will render an error, yield an error. It didn't because it doesn't render anything because there is no color in the position value in the uniform variable. I'm going to write color here because I don't want to name it position. Okay, because get some water, guys. I'm keep I will keep going on with the tutorial step. Be right back. So I'm back again, and let's keep on going with the uniform part of the tutorial. Declare a uniform vec for our color in the fragment shader and set the fragment's output color to the content of this uniform value. It's fine. Since uniforms are global variables, we can define them in any shader stage we'd like. So how to go. Thanks a lot. So no need to go through the vertex shader again to get something to the fragment. We're not using this uniform in the vertex shader, so there is no need to define it. Okay. if you declare a uniform value, isn't it? The GLSL, the compiler will silently remove the variable from the compiled version, which is the cause for several frustrating errors. Keep this in mind. Okay, the uniform is currently empty. We haven't added any data to the uniform yet, so let's try that. We first need to find the index/location of the uniform attribute in our shaders. Once we have the index/location of the uniform, we can update its values. Instead of passing a single color to the fragment shader, let's spice things up by gradually changing color over time. Oh, time value. It's using time value here. First, we retrieve the running time in seconds via glfw get time. Then we vary the color in range of 0.0 to 1.0 by simply getting the sinus. Okay. And store the result in green value. Vary for the location of our color uniform using get uniform location. Okay, we supply the shader program and the name of the uniform that we want to retrieve the location from to the query function. If GL get uniform location returns -1, it could not find the location. Lastly, we can set the uniform value using the GL uniform 4F. Does not require you to use shader program first, but updating uniform require you to first use the program by calling GL use program because it sets the uniform on the currently active shader program. What does that mean? Shader program is activated and we set the uniform after. That finding the uniform location does not require you to use the shader program first. So if you want to find it, find where our shader program is, want to use this function, we could use it, could call it before GL use program call. Okay, but we have to use the GL uniform 4F after the GL use program. Yeah, I see. What's in the green box? Because OpenGL is in its core SE library, it does not have native support for function overloading. Wherever a function can be called with different types, OpenGL defines new functions for each type required. GL uniform is a perfect example of. The function requires a specific postfix for the type of the uniform you want to set. A few of the possible postfixes are F, E, I, 3, F, F, V. We get it, it's float, integer, unsigned integer, 3 floats, float with vector. Here it is 4 floats. Whenever you want to configure an option of OpenGL, simply pick the overloaded function that corresponds with your type. In our case, we want to set 4 floats to the uniform individually, so we pass our data with via GL uniform 4F. Could have also used V version, but it sets the color for everyone the same. And that's what I don't like it. That's why I don't like this. If I want to set the color differently. I mean, I can use this, but it doesn't bring me anything here in this point. Maybe bring anything to me. I don't know. It shouldn't. it's uniform, it's global, it wouldn't change anything. I could implement something like a rainbow, simply changing with time like this, but let's try it. Okay, let's try it. Let's try the uniform variable. We get this color to set the time, set the color with the time value, but we're going to change the color for each vertex, for each triangle. Shader program, yes, update the uniform color. What uniform color? It's green. Okay. Value is, oh, this is the uniform variable. It's color. It's color in our program. Okay. What I'm going to do, I'm going to set an out. I don't want this anymore. I want to set an output here. Out vec3. It's vec4. I don't care. Color offset. This color offset will be then inputted here. Will then be input here. Will be put in here. In vec4 color offset. And a new line. Yes, and what we're going to do is simply, can I see what normalize does? GLM normalize, if there's a function that's called normalize, does GLM normalize? Should, my understanding and in my logic, it should put the vector values in a scale from 1 to 1. There is one. The documentation of LM. And normalize, what it does. It normalize returns a vector in the same direction as x but with length of 1. The same direction, so we need to get absolute value after all. Yes, how do we set the color offset? We simply did he color offset. This is the apps value, and as the alpha we get 1.0. But what I want to do here is not use the normalize function, but repeat it. So if we get, I will show you what I want to do. Yes, okay. I want to define a new color, final color. Final color will be then set with color plus color offset, but we will call but we will change color offset. So this is going to be set to the frag color afterwards. We are going to define final color here and how to create the final color. The final color will be set through the it's a vec4. It will be set through the color, uniform variable color x, color y, color z, and color w. But we're going to use the color offset here, color offset, which is a positive value, and simply add them together and use modular function afterwards. But can you like I need to check if modular functions in modular function see floats. I don't know how does it function with floats. Fmod can use the fmod function from the standard mod library. It's prototype standard double fmod. Does it implement it? Let's see. Let's use fmod. Fmod. The first argument is this. The second argument is 1.0f. Simply the same in the y component. Y, and the color at z component is always 0 with the color offset. So we're simply getting colored set here, and the v component is always 1.0. So there is no value to alter that value, alter this. Let's save it, compile it, and finally try it. Okay, we have errors, of course. What is absx? Oh, don't define it. Windows, pos, POSIX. OpenGL does not, shader fragment does not define the global function fmod. Okay. Edge. OpenGL fmod. Here. OpenGL fmod. Mod. Value of the parameter. So another, okay. Okay, let's compile. Tar. Does something change? Yes, it changes. But the modular, the offset is not implemented. It simply does. Oh, of course. I don't set the color to final color in the fragment shader as my output variable. So when I set final color here, it should work, I suppose. Nice. Nice. Look at this. This is so it seems so dumb. Seems so dumb. But we have managed to do something using the what do you call it, the vertex data. I mean, it seems nice. I guess it seems okay. I guess. Let's see why this doesn't function as I wanted. I mean,
What did you do?
I'm using time and as a science function to change the color, and then I'm creating offsets to.
Oh my god, it looks
Yeah, it's
scary.
weird. To change the value of the color for each vertex.
So scary.
P on P. Now, okay, we've managed to do something. And I would like to see what as if I type it here. Type those two. I want to see if the polygon mod changes, because it's really dumb right now. The color doesn't change. Read it. Start it. Does this P still does nothing? Still does nothing. Should we clear it again? I mean, it is okay right now. I like it. I don't hate it. From the progress we have made, I can simply go and yeah, this is the animation this guy has. So what we have done, I will explain it again. We have was it like when I zoom it? Okay. We get the time value from the system, from the system, I guess, as a double. I know this. I don't know the value seconds unless the time has been set using glf. W time. It measures the time elapsed since glf. Was initial function and W set time are helper functions on top of time frames. System dependent, but is usually on the order of a few micro or nanoseconds. And this is simply converts the value to sinus values, and this makes sure it's in the positive positive area, positive interval. I don't know. Let's see. Let's try to create blue value here from the cosine. Give value as a cosine function. I should change this probably. Let's see. Get errors. Get the behavior you want. Oh, feel it. This is some weird stuff going on. Yeah, this is nice. It's like a sinus function. Go. More attributes. What are these? You have accomplished this. Yeah, we have some stuff. It's fine. Let's go. Keep on with the more attributes. What are more attributes? We saw in the previous chapter how we can fill a VBO. What is a VBO? It is a vertex buffer object. How we can configure vertex attribute pointers through the VAO. And how do we store it all in a VAO? This time we also want to add color to the vertex data. This is pretty nice. Thank God for this section. We're going to add color data as tree floats to the vertices array. We assign a red, green, blue to each of the corners of our triangle respectively. Nice. That's what I've been searching for yesterday night. And this is so simple. Since we now have more data to send to the vertex shader, it is necessary to adjust the vertex shader to also receive our color value as a vertex attribute input. Okay. Note that we set the location of the A color to attribute to 1 with the layout specifier. This is set to 1 as location, and this has the name A color. Out vector our color. This is our color. Output A color to the fragment shader. Okay, fragment shader will then get. We have already done this. GL position is set through the vec for A pos with 1.0. This is buffer. Sorry, I'm lost between the color and the GL position. Since we have we no longer use a uniform for the fragments color, we now use the our color output variable. We will have to change the fragment shader as well. I've already done this, the passing, because we added another vertex attribute and update the. So, because we did these color thingies, we have to say that we need more space to get our vertices, and we will make it in the stride section or the offset section. Let's see, what is it? The position attribute. This is bounded to the location 0. It uses 3 values of float. What was it again? It isn't normalized. It shouldn't be normalized. And that. Right, what is stride? Stride is where we are going to get the other value, the next value. It is after the RGB values. Therefore, we are using 6 times size of float. Before, we have used 3 times size of float. So, and it's sorry, and it starts from the address 0 here, from the offset 0. And the color attribute is written into the array number 1, array location number 1, vector number 1. It is written 3 by 3. It uses GL float. It shouldn't be normalized. The next value after the value read is 6 values after, and the offset is 3 floats after. It starts after 3 floats, keeps on with 6 with the stride of 6. So we can implement this quickly in our code. The vertex shader gets another input here between. This is called layout location equals 1 in vec3 RGB. I will call it RGB, and as an output we set simply color offset. We're fine. We set color. I don't like color offset. We simply delete uniform comment that out to show that we have implemented it, and as an input we get color. Okay, these two match. We don't do anything with the color offset or apps value of the position anymore, but simply set the output variable color to a new vector for, which is created from RGB and 1.0f. Create a new line. Yes, this should work. And here the final color is not determined by the offset or position or the uniform variable color, but through the input variable color. Yes. And now we have to we have to alter our vertices array and put some color values in this array. Before I do that, I will do that first. Yeah. And come to that later. The other one. I'm going to open my modeling scene, and that I will put here. Oh, okay. I don't want this. A file. I don't want to change. Now to get in and open my pizza mode page, so that I will simply my modeling scene. View it in full page mode. What do you guys see? Is the modeling page and nothing else. This is what right now. I will simply add the color values to the vertex values. Yes. Enough. Starting now. So we have our 0.0. Got it F as our origin. So the origin, it's starting from origin. We have different triangles. So we will give color. I want this to have the color blue. And if I give these to blue too, I should get a blue, neatly blue triangle here. No? Yes. And if I give the vertex number 1 the color red or green, I will get bluish and red/greenish colors as it's interpreted. So yes, I will give the vertices number 2, 3, 5, 6, 8, 9, 11, and 12 the colors blue, and the others will get any color they want. Let's open the and let's hide the tasks. Let's go. The colors. What did I say? I said the number 1, number 0 gets the color 1 0 what am I saying, RGB 0.0, 0.0 and 1.0, and these are colors, and then the first one gets whatever we want, but the second one gets also blue, third one also gets blue, fifth and sixth ones, fourth, fifth get blue, seventh, eighth, eighth and ninth gets blue, 10, 11th and 12th also get blue. Oh, there, comma here. Yes, the middle ones get whatever color they want. Let's say they get white. Let's say that they get white. Did I see? Oh, it. Yes. So we have set our vertices and their colors. We will now set the settings. We will tell the GL to get colors as we want them. So this vertex attribute pointer is changed. This gets 6 times size of float, and we introduce another vertex attribute pointer here. This is the location 1. This is the location 1, and it takes 3. It is a float. It is a float. And it shouldn't be normalized. It has stride 6 times size of float, and it begins after 3 times of size of float. Not float. Yes. What is this? Parentheses. Yes, this should go. Okay, let's keep reading. The first few arguments of GL vertex attribute pointer are relatively straightforward. This time we are configuring the vertex attribute on attribute location number 1. The color values have a size of 3 floats, and we do not normalize the values. Values are not normalized. We could have, never mind, since we know how to vertex attributes, we have to recalculate the stride value. I mean, we have different values in the array. Get the next attribute value, example, given the next x component. Sorry, but never mind. Okay, we get y the stride is set to 6 and y offset is set to 3 times size of float, and we can compile it and see if we get the wanted solution. What is this? To press F. And this is more like it. This seems more like a fan or a wind turbine. I would like it to turn actually. I don't know right now if I have the brains to do it because I'm pretty tired. Yes, let's see. Let's read it. The image may not be exactly what you would expect. It was exactly what I expected because, like, I knew I knew it was going to interpolate it. Based on these positions, it interpolates all the fragment shaders input variables. Say, for example, we have a line where the upper point has a green color and the lower point a blue color. If the fragment shader is run at a fragment that resides around the position at 70% of the line, this resulting color input attribute would then be a linear combination of green and blue, to be more precise, 30% blue and 70% green. This is exactly what happened at the triangle. We have three vertices and thus three colors, and judging from the triangle's pixels, it probably contains around 50,000 fragments. Sure. When the fragment shader interpolated the colors among the pixels, if you have it, take a good look at the colors, you'll see it all makes sense. Let's hit the blue first. Hit to blue. The blue. Fragment interpolation is applied to all the fragment shaders. Okay. Ah. It explains how to use separate files for it. I'm relieved actually that we have managed to complete this tutorial. This is just jibber jabber. I will read it, but I want to change the colors. I don't want them. Let's keep reading it. Writing, compiling, and managing shaders can be quite cumbersome. As a final touch on the shader subject, we're going to make our life a bit easier by building a shader class that reads shaders from this, compiles and links them, checks for errors, and it is easy to use. Also gives you a bit of an idea how we can encapsulate some of the knowledge we learned so far in the useful abstract object. We will create the shader class entirely in a header file. But there is no any shader file. This is weird. By defining class function. How does it do? Does he do it? Class shader. Public. Program ID. Constructor. Text path. Fragment path. Use. That it. Does everyone do it like it? Text code. Fragment code. See. Know what this does? We say preprocessor. Directives at the top of the header file. Using these little lines of code informs your compiler to only compile this header file if it hasn't if and def. Add a little. So we also add several functions or likes a little user with the shader program, and all set functions carry a uniform unit location at its value. Nice. Should implement. Okay, see a reading from file. We are using C++ file streams to read the content from the file into several string objects. Vertex code, fragment code, if stream header file, if stream objects count. Okay. Open files. Stream opens them. String stream are defined. Shader stream buffers the shader files input, the shader file buffer, read buffer, then put into the shader stream. And then the files are closed. Have the buffers in shader stream. Fragment shader stream. Convert stream into the shaders. Fragment shader of vertex shader are converted into codes, into strings. Afterwards, if there is any error, we are catching that. And if there is no error, simply setting the shader and frag shader code. And after that, our code comes in and creates the shaders. What is shader? Shaders using the V shader code and F shader code. It then creates a program. We have created our program. ID. Unsigned integer. Okay. This is the implementation of shader class. I see. Attach shader, link program, errors if access shader, the link to program, and the use functions program. I will I will implement these functions in the next chapter of the stream. For any that boolean reform 1e, 1e, 1f. I will also set vec. I will also make a set vec. And yes, the shader is created like this. Here you're free. Quite named it as fs. I'm going to get word and frag. So yes, OpenGL, the class shader and the implementation. Is simply init. Shader s. This is the shader s header file. Implementation is in the header file, so we implement it in the same header file. I will do it the next episode, and afterwards we are going to continue with the next step of the tutorial, which is the textures. We are going to use textures to paint our triangles, paint our pizza, wind turbine, fan, whatever, what do you call it. We're going to learn what maps are. We're going to learn how to create and load textures, how to generate textures. And also we are going to pass these vertex values within the vertex array probably, as it's seen here. And yes, afterwards going to be ready to paint whatever we like and however we like in the OpenGL. After that, we have transformations, coordinate systems, and camera. We are getting pretty good. We're getting pretty good progress here, I would say. And we're not graphics programmers yet, of course, but for the first 4 sessions, I think we have come a long way. We have learned a lot. And after I'm ready, I'm finished with the getting started section, I will write my own review of the tutorial. I will determine what I've done for each step in the stream, and I will write it as humanly understandable as I can. And yeah, after that we'll keep going on with the lightning. We'll see more advanced concepts like the light sources or the effects of the light sources on the objects. Today I'm done. I'm pretty I'm pretty tired, I would say. So see you in the future.